a picture of the instrumented element. First, you have the pressure sensors marked as red circles on 1, 2, 3, 4, 5 different levels. And then you had the pressure sensors marked with circles were mounted on the same levels as the strain gauges. The strain gauges are marked as black rectangles with red rims. And as you can see, they're mounted very close to each other. And finally, the ones that marked as crosses inside red boxes, they are the load cells on 3 different levels. So we should focus on the pressure sensors and the loads and the strain gauges mounted on the same levels. And they are measuring pressure in 2 different ways, either with a membrane, pressure sensor, or strain gauge. The pump hose, it took 4 concrete batches to fill the section, and each lift was 1.5 meter in average. The position was horizontally fixed during each casting, alternately 3 meters from the right and 3 meters from the left end. It's marked 1, 2, 3, 4. So it wasn't moving. We poured all the concrete from one side at a time. The mix design, it's consisted of Portland limestone cement, limestone filler, of course aggregate, natural sand and crushed, maximum size 16 millimeters, and water cement ratio, as you can see, 0.50, and plasticizer, and of course air entraining agent. We had quite an amount of powder, so the water powder ratio was 0.33, and we wanted to have a lot of powder. So as you can see, it's a lot of limestone filler in order to get the thixotrophy. This is the first, after the wall was finished, 2 of the instrumented elements were mounted together and filled with water in order to verify the pressure sensors. The x-axis is pressure and y-axis is height. As you can see, it's a very good correlation between hydrostatic pressure and pressure sensor values. So this was in order to verify, to control the pressure sensors, and it's almost too perfect. So now, after that, we knew that they were okay. This is the first of the 2 relationships studied: pressure sensor values versus strain. And as I said before, we had 3 elements, but this is an example. This is element number 1, and it's a certain level. It's strain 600 millimeters and pressure 530 millimeters. So this is one example of all the measurements. The x-axis is center pressure in kilopascal, and y-axis is strain. And this is very interesting. As you can see, the slope varies very little between the castings. That means that you have very good correlation, very good repeatability between the castings, between the dates. In this slide, you have 1, 2, 3 different castings. And the fourth one, the red one, is the calibration with water. But the same slope, we were almost amazed on how good repeatability it is. So, and the other thing you can see is that the R2 factor is an example how well the points are following the lines. This is another example. This is another element, number 3, and another level. The trend lines and R2 factors have been added to show how well the trend lines are connecting the points. An R2 factor is between 0 and 1, where 1 indicates that each point is on the line. As you can see, R2 is 0.99, almost like 1, so very good correlation. This table shows the slope for all castings, elements, and levels. As said before, the slope in one specific element and level varies very little. As you can see, one element, this is element number 2, and it varies very little. Overall, the mean value is varying between different elements and levels. As you can see now, these are mean values of all the different elements and all different levels. And why is that? Well, it's probably depending on some structural aspects, varying load width between levels, not exact placing of sensor and gauges, and varying bending stiffness of the horizontal steel profile. The intercept and R2 factors. The intercept is limited to only 5% of the maximum strain values. For all castings, some sources of error could probably explain that. And the R2 factors for all castings varies between 0.9707 and something has fallen off there. The next value is 0.9997, which is almost 1. The picture is the slide is damaged, so it's almost 1. I wanted to compare my measured strain values with computed ones using a simplified model. The upper figure shows the lower part of the formwork element. In the lower figure, the horizontal profile is replaced by a corbelling beam on 2 simple supports. The load width is 300 millimeters, which is equal to the distance between the profiles. The equation calculates the strain as a function of pressure. Assumptions have been made, of course. Pressure is constant over the load area. Plywood has no impact on the strain. And linear relationship between pressure and strain. As seen, the model computation results in the slope value of 6.4. And if you remember the table before, we had values almost 6.4. So this means that the simplified model did work. This slide shows an example of the relationship between pressure sensors values and tie bar tension force. This is element number 1, pressure sensor level 530 millimeters. As the x-axis is sensor pressure and the y-axis is tie bar tension force. As you can see, there's a good repeatability between the two castings and the water-filled formwork. The curves are continuous, bending upwards, but that is logical due to the interaction between the three tie bars. I will skip this because this is not that important right now. In this, it will be the next time in my next paper. I will develop finite element methods, and we have been calculating on the strain, but it's too early to say something about it, so I will skip this slide. Overall evaluation of the project. I interviewed the site foreman and the site manager with focus on cost, production technique, and working environment. The total cost for the inner and outer wall was approximately 2.5 million euros. The use of SCC enabled a decreased production cost by about 10% thanks to the short production time. The improved working environment was very often highlighted in the discussions with the contractor. Can you imagine to stand there 1.4 kilometers, 6-meter high wall, standing there with pokers and vibrators? It's almost too impossible to think about. They were also very satisfied with the finished surface quality. This is one of the finished sections seen from above. Concluding remarks. We had good correlation between pressure and tie bar tension force, but the most important thing about this paper was number 2, very good correlation between pressure and strain. Also very good repeatability from day to day in the same element and level. Significant advantages for strain measuring, such as easier handling, gauges, and cables remaining on formwork after casting. Easy to disconnect cables. So how can we use this? If you don't know your concrete, I think the robustness is varying, as you know. You don't know how the concrete will, the properties when the concrete arrives at site. So if you don't know your concrete, know your formwork. The pressure strain slope at selected levels. How do you get to know your formwork? Either you calibrate with pressure sensors, or you have a preceding static analysis before the first time. Measure strain, as I did, and control the casting rate. So you have to be, you have to monitor the computer with of course, during your casting. But as I did up in the project, I had a contact with the ready-mix concrete manufacturer and the pump driver, so I could all the time tell them to vary the casting rate. So it worked very